Welcome to your interview. The first question is, what's the difference between C and C++? You can do object-oriented programming in C++, whereas you can't in C. You just failed the interview. Please leave the building. If you think that the interviewer is being dramatic, think again. Today we are going to be putting an end to the myth that you can't do object-oriented programming in a classic procedural language by emulating the 4 pillars of object-oriented programming in C. And along the way, you will gain a deep understanding of the philosophy behind the core OOP principles: encapsulation, abstraction, inheritance, and polymorphism. Because object-oriented programming is a paradigm, and so while C doesn't have built-in syntax to directly support OOP features like classes or visibility keywords, these patterns can absolutely be expressed in C. And I believe that doing so will even help you learn about these concepts more deeply when looking at them through a low-level lens. Let's get started. We're going to be coding this game together, which you might recognize, but for copyright reasons, I changed the characters. And what I want you to do is think about something for me. What OOP principles might you use to implement this game? Let the game begin. First, we enter the number of players. Let's choose 8. It's nighttime. The basic premise is it's bears versus everyone else. The bears want to win by biting people during the night. Player 1 is going to press enter. Now it shows them their role. They are a townsperson. Player 2's turn. They are a bear. Bears also have a slightly different output. It shows who the other bear is. They select a player to bite. Player 3, another bear. He can see who the other player bit too. Player 4, activist. The activist will select one person to ban from voting during the day. Player 5, townsperson. No special ability there. Same with player 6. Player 7, healer. They can choose one player to protect from the bears. And finally, player 8, clairvoyant. They can select one player to see their role. Now the night round is over and it's revealed that player 5 was bitten by the bears. It's daytime and each player takes a turn to vote. In case you've genuinely never seen this game before, the idea is you want to try and work out who the bears are amongst your friends and vote them all out. 2 cannot vote because they were banned by the activist, and the activist gets a 50% chance to get a second vote. Voting is over. Player 3 was eliminated because they got the most votes. And this keeps going until either side wins. Note there are some caveats. The healer can't protect the same person 2 nights in a row. The activist can't ban the same player 2 nights running either to prevent the endgame getting too stacked. And if the healer is eliminated, like they have been here, they get a 50% chance of healing themselves and coming back. Before you get addicted to playing this incredible game, you're ready for the first pillar, encapsulation, not to be confused with the incredible tech YouTuber Encapsulation. Encapsulation refers to enclosing data together with the functions which operate on it in one single bundle, an object. In languages like C++ and Java, the blueprint for defining an object is commonly known as a class. It defines the object's state through its member variables and its behavior through its methods. Since the methods and state are now bundled together, a powerful action you can take is to restrict outside access to the object's internals. In other languages, you may have seen access modifiers like public and private which achieve this. This ensures the object can only be accessed and altered in the ways which are within the rules defined by that object. Alrighty, encapsulation in C. Let's try and simulate this principle. Begin with just a main function in main.c. I also have some handy util functions off in the util directory, but don't worry, all this code is on GitHub, you won't miss anything. First, we ask the user to input the number of players. This helper function from the util file just grabs a valid int in that specified range. Then, of course, we want to start the game loop. The game is a perfect candidate for the first class-like structure we are going to emulate in C. Why is that? The game is going to have a lot of internal state. This includes the following: the number of players, the number of bears and townspeople left throughout the game, whether it's a night or day round, and then information about the current round, including the array of bitten players and the number of bites delivered this round, the player who has been healed this round, and finally, the array of player types. But ask yourself, does main really need to see all of this internal state? No, in fact, main shouldn't have direct access to that data because the game object itself should be responsible for its own state. Main shouldn't be able to go and muck around with the game internals all willy-nilly because it might break something the game depends on. Data hiding is one of the core encapsulation concepts. We want to protect the game's internal state from unintended modification or inspection by only allowing access in a controlled way via public methods. So let's come up with a public interface for the game by considering what main should be able to do. It should be able to construct a new game instance, feeding in the number of players the user specified. This will initialize and allocate memory for the game and return a pointer to that instance. 2. Kick off the game loop for that game instance. And 3, destroy that game instance when it's done, freeing everything. But how do we create this object blueprint in C? Let's start with the idea of the class itself. Remember, at its core, a class just bundles properties and methods together that relate to that entity. Now, C doesn't have classes. If it did, this would be a very boring video. But what C does have are structs. These allow you to group a set of variables into a single type. And when a struct is allocated, the data is all stored in one contiguous block of memory, with padding, of course. Let's define the game struct to store the game internals. For the moment, we will do it in the game.h header file so that it can be included in main. Now you see in main, we can access these struct members. That's the data grouping step of encapsulation, bundling related data using structs. But now, how do we emulate the data visibility concept, whereby the game's internal data is private and main can only access data and functions intended to be public? Because remember, we don't actually want main accessing all of this internal state of the game object. This can be emulated through clever use of header files. Each entity, or class in quotes, has its own header file exposing the interface intended to be public. And it has its own corresponding C file for the implementation details, as well as definitions intended to be restricted from outside access, i.e. anything private. Imitating public methods in C is simple. Add the function declaration in the header file and define it in the C file. Any file that includes the header can then call these methods. Private data in the game struct is a little trickier. Private data can be emulated by making game an opaque type. An opaque type is one which has a forward declaration, so it is known to the compiler, but its implementation details are hidden from the outside. The forward declaration will be placed in the header file, but it's left as an incomplete type as the struct's full definition is in the game.c file. Let's see exactly what this means in practice. In the header file, instead of exposing our beautiful game struct, we'll instead forward declare the opaque type, like so: type def struct game game. This is incomplete because only a forward declaration will ever be in the header. We move the actual definition of the struct to the game.c file, so only game.c can directly access the internal data. Essentially, game.h is our public interface, and game.c has the game's implementation details which are intended to be private. Now when main includes game.h, Node can no longer access the struct members directly. Why not? Because this incomplete type is all that has been included in main, which does not reveal the game struct's internal layout. This means that the compiler doesn't know the layout of the struct, and by extension its size, so it can only work with pointers to it and not its internals. Recall we have one more thing to do, which is create the functions that we intend to be similar to the public methods. Copy the function prototypes of the methods we discussed earlier into the game.h file and put stubs into the game.c file. You see, main can call these functions because we've included game.h, giving main access to this public API. Congratulations! You've effectively mocked your first class-like structure in C. To summarize, we can refer to the game type and use pointers to it, but cannot access its struct members or instantiate it directly by value. And we can call the functions declared in game.h, whose implementations are in game.c. Let's now bring this to life a bit by implementing some of these public methods in game.c. Let's start with the game constructor function. A constructor in OOP creates an object instance. In our case, this takes in the number of players and will return a pointer to the allocated and initialized game. Malloc it to plonk it on the heap. Then we have as follows: num players equals the num players just passed in, is night equals 1, we're starting as a night round. Num bears left equals num bears. I've defined that as a macro, so you can just use it everywhere. Num townspeople left starts as the total number of players minus the number of bears. Bytes this round and player healed are all state which resets each round. So we can move the logic to set those to another method, so we can reuse it at the end of each night round too. Finally, players. Let's leave this for now, the players array, because we're going to look at player types when we cover abstraction, and I'm going to comment out this players array so it just compiles for now. Okay, back to this helper function which resets the game state. This can be considered like a private method because we don't wish for outside code to access it. Don't put this function declaration in game.h. That way, any other file, including the game.h header file, won't have this function prototype added to its translation unit. But one problem is we can just manually put a forward declaration to this helper function in another file and still call it. So this is kind of like fake private in the sense that you're trusting people not to do this. To communicate this privacy further, you can use the static keyword. The static keyword here gives this function internal linkage, which means it is only visible to the translation unit in which it was defined, game.c in this case. A translation unit is typically a single .c file after pre-processing. Now, even if I try to declare this function in game.h, see how when I try to call it in main now, it fails at link time because the symbol is not exposed outside of this game.c file. So marking functions you intend to be private as static is a good way to further enforce access restrictions in C, as it restricts them at the linker level too. Okay, let's delete that. Currently, there will be memory leaks, of course, because we mallocked the game on the heap. So obviously, we need to complete the game destructor function urgently to clean up this memory. You know the drill, free. When we actually allocate the players array, we'll need to free that too in this function. I've added a bunch of print statements everywhere, so now when we run it, you can see the program flow a little bit. On a final note, you might think that this doesn't quite feel like the class methods you're used to, because in other languages like Java, you can call a class method on the instance like game.loop. In our C version, we need to actually pass the game instance into the game loop method. But I don't think this is anything to lose sleep over. For example, if you are coming from Python, you can see Python methods also explicitly declare self in the parameters of a class method, and this gets implicitly passed in when a method is called. But a key difference here is that the game struct doesn't have its functions attached to it. So our encapsulation bundling in C is, like I said, coming from that conceptual grouping of corresponding .h and .c files. Then the data visibility behavior emerges from our other tricks like opaque types and the use of the static keyword. This is now the end of part 1, encapsulation. Here's what we have learned. Encapsulation consists of two main concepts: bundling and closing data together with the entity's functions which operate on it in one single conceptual bundle. Data hiding, restricting outside access to object internals. Bundling in C can be imitated by placing all related object data into a struct, grouping this data alongside object functions which operate on the object, i.e. methods, in a single .c file. Data hiding of the struct internals can be encouraged by declaring the struct as an opaque type in a corresponding header file. Functions intended to be public and used everywhere have their prototype placed into this header file to be included elsewhere. Functions intended to be private can be implemented in the .c file directly and omitted from the header. Marking these as static gives them internal linkage to further communicate the intention for this privacy. We need to create a player type, so this brings us to our next OOP concept, abstraction. Abstraction is the principle of hiding specific implementation details, instead opting to reveal only what's really necessary to use that object. For example, when a player is eliminated from the game, does the game class want to deal with all the internal behavior like setting is alive to false and checking if they are a healer who can heal themselves and so on? No, of course not. The game just wants to call player eliminate player and move on with its day. Under the philosophy of abstraction, we would abstract away the internal complexity of how player works and provide only a simple interface so objects can interact with it more effectively. Then the concrete player types can provide their own implementations behind those operations. One way to model this is via abstract classes. An abstract class can't be directly instantiated. Instead, it reveals the interface through abstract methods. Concrete subclasses must then extend this abstract class and implement these abstract methods. Abstract classes can also contain fully implemented methods too, which are shared amongst all the subclasses. These can be overridden by the subclasses if needed. In our shape abstract class example on screen, we have an abstract method to be overridden, getArea. This means the user can simply call the getArea method, and the actual concrete subclass is responsible for implementing the details behind calculating that. Anyway, I'm going on about this because player is going to be a bit like an abstract class. Of course, C doesn't have abstract classes. Again, it would be a very boring video if it did. But we are going to try and approximate the behavior. We don't want to be able to instantiate a player directly. Instead, a player is going to be similar to a base class, and all the specific player roles, the subtypes, are going to build on top of it, implementing their own behavior. Inside the player object, we want player ID, role, is alive, 1 if they're alive, 0 if they're not alive, and some round specific properties, is bitten and can vote. And then we want our C equivalent of public methods to get and or write to some of these values. Remember, this means the prototype should be included in the player.h header file. These functions will be the same for every player subtype. Time to implement this so far. So in a new player directory, create the player.h and player.c files. And remember, it is this grouping of corresponding .h and .c files that we use to contain the blueprint of our object. First, define the player data. Remember, structs in C can hold data, so we'll place our member variables inside the struct in the header file. For now, we'll keep everything public exposed in our header file. And define the role enum. Free tip of the day, if you let the enum auto increment, i.e. the enum is just ascending ints under the hood, and add one more value to the end of it, this will be the count of roles in your enum. Then we want to implement some of these public getters by putting the function prototype in the player.h file and the details in the player.c file. These all operate on an instance of the player type. Another thing to implement is that we have these player roles here in an enum. We'll want to output those as strings at several points in the game. So let's create another function called player role toString, and it's going to take in the role. This should be accessible everywhere, so put its function prototype in the player.h file too. However, notice that this doesn't need to take in a player instance to work. This is kind of akin to a static method in OOP, which is a method that is included in a class because it's related, but does not operate on an instance of the class. Now remember, we want to discourage instantiating a player object directly because we are trying to imitate the concept of an abstract class here. Players aren't really real. Only concrete implementations like bears and activists should be instantiated. So you might have noticed that we can communicate this in C by not giving it a constructor function, but instead, let's provide this initialization function. This will make life easier when the subtypes actually do need to be instantiated. The concrete subtypes, like activist, healer, etc., will allocate memory for the object instance in their constructor functions and pass it into the player initialization function to set some of these member variables. I've named it super so the Java devs feel more at home and to remind you what we're echoing, which is like a base class constructor. Notice that player ID and role are public member variables because whatever, they're used everywhere. But notice is alive, is bitten, and can vote are protected. This is a new access modifier and means the concrete subtypes which extend player should have access to this data, but not other types like the game type, for example. So how on earth do we approximate this behavior in C? Let's revisit the player struct. Currently, this has all the data exposed in the header file. But then how do we enforce or at the very least communicate that the variables intended to be protected should actually be accessible only from the subtypes and nowhere else? It's not as easy as making player an opaque type as we did for the game struct. Why? Because 1, doing so would make the player fields inaccessible outside player.c, but we are going to be making .c files for all the player types who also need to access these member variables too. And 2, there's kind of a splitting of the struct that needs to happen here between public fields and protected ones we intend only for the subtypes. So making this an opaque type hides the internals of the whole player struct, not just the protected fields. It kind of doesn't work for us because we want role and player ID to be public. Additionally, look at our player init function. We'd also want this to be protected too, since only the subclasses should be initializing those member variables. Tricky. A way to achieve this kind of splitting up of the struct into public and protected segments is to adapt a PImpl idiom-like pattern, meaning pointer to an implementation. This is a C++ concept, but we're going to adapt it similarly for our use case here. Within our public player struct, instead of having the member variables intended for subtypes only, we are going to include a pointer to a forward declared struct, player protected. This is an opaque pointer. Here, player protected is an opaque type. Remember from encapsulation, that means it is only declared in this header file as a forward declaration without details about its inner structure here. The actual player protected struct needs to have those internals defined elsewhere. Now, other files, including the player.h header file, can access role and player ID within the player type, but it cannot access any member variables inside protected because the player protected in a structure is defined elsewhere. Essentially, protected is just a handle. The next problem is, where do we actually put the player protected definition that's not inside the player.h public API? Because remember, we don't want everything accessing this. We cannot put it inside player.c because then even the child subtypes in other files cannot access it. One thing we can do is create a new header file for protected data called playerprotected.h. We can put the player protected struct definition in here, as well as function prototypes for any protected methods. Now child subtypes only need to include the player protected header file, but everywhere else includes the regular public player.h file for access to the public API. Note that this doesn't strictly enforce protection, since technically any file could include the player protected header, but it does communicate intent better and helps structure the program in a way that mirrors the object-oriented design we're going for. So create the player protected h header file. In here, we will include player.h so we have access to the rest of the player API. Then define the player protected struct, with the members being the variables we intend to keep protected, i.e. visible to the player subtypes only and nowhere else. And back in player.h, replace those same struct members with a pointer to a player protected struct, which we will include a forward declaration of. Remember, this is our opaque pointer. Do not include player protected.h in player.h, because then any other file, including player.h, will also gain access to the contents of player.protected.h, which we intend to keep protected from outside access to all but the child subtypes. So yeah, that would completely defeat the purpose. We also wanted to communicate that the initializer should be protected too, so move its function prototype to the player protected header too. But notice this function's definition will need to change a bit, since we don't set these member variables directly inside the player struct anymore. We need to allocate the player protected struct first. Now we can initialize these member variables. Note that I'm mallocing this, so this must be freed in a corresponding destroy function so the players don't leak memory everywhere. But we don't have to worry about that just yet because we've not actually created any player subtypes yet. Since these member variables are in this protected struct member now, we have access to them through the protected pointer in all our methods. And one final thing we can squeeze into this chapter is that now the player object is all set up, we can include player.h in game.c. Remember, do not include player-protected.h, as that is only intended for the child subtypes, activist, healer, and so on. Now we can uncomment the player array in the game struct. And in the game constructor function, let's malloc this array to be the number of players in our game times size of player star. Leave it for now because we don't have any concrete players to initialize yet. And free the player array in the game's destructor function. Quick compile and quick play to check there's nothing nasty. Looks good. Now we have simulated a player base type who is meant to mock the behavior of an abstract class. So this is the end of part 2, abstraction. Here's what we've learned. Abstraction is the principle of hiding specific implementation details, instead opting to reveal only what's really necessary to use the object. A nice technique to champion this is using abstract classes. These cannot be instantiated directly, but instead must have concrete subtypes extend its functionality and implement its abstract methods. Protected member variables and methods should only be accessed by subtypes. One way to communicate this in C is to put protected struct definitions and function prototypes in a protected header file, which is then included only by the subtypes. Structs can be split into public and protected/private member segments by adapting the PImpl idiom. Include as a struct member an opaque pointer to a struct defined elsewhere, so code including the public header cannot see its internals. This is incredible progress, but the player type is feeling a little abstract. I suppose that's the point, but we want to create these concrete subtypes. It's time for the next pillar, inheritance. Inheritance is the concept of new types building on existing ones. It involves subclasses inheriting the attributes and methods from the base class. That means the parent class defines the common interface which child subclasses can then extend or override, enabling code reusability and customization. For example, all polygons have a numSize property, so the base or parent polygon class can define that once and then all its subclasses will inherit it. This is powerful because you can then add a new class later who inherits from polygon, and that too will automatically get the numSize property. No need to rewrite shared logic. In our case, the various player roles need to be their own types, which inherit from the player base type. In this inheritance part, we will have three main goals. 1. Player subtypes need to inherit or reuse all the player member variables and functions without us needing to re-implement them. For example, a healer should have a player ID member variable because that is inherited from the player type, but we don't want to explicitly define player ID in the healer struct. It needs to be passed down from the player type. Therefore, the subtypes need to inherit all functions and member variables of the player type. 2. We need to be able to treat all subtypes as the base player type. This means casting player subtypes back to the player parent type known as upcasting. Remember from the abstraction pillar that the game object will be interacting with the players through public functions in the player API. These methods accept a pointer to a player type, so we need to be able to treat the player subtypes as generic players through upcasting. 3. We need the player subtypes to be able to build upon the player abstract type. They must be able to add their own public and private methods, and they need to be able to add their own additional member variables too. Any methods tied to the subtype must act on an instance of that subtype. As a side note, this means we should also support downcasting, casting the player type to its more specific subtype, because the game only has an array of players. More on that later. Before we learn how to do this in C, let's get prepared. So make a new directory. I call it PImpl because it will store the player implementation or subtype code. Add the .c and .h files for each role type: activist, bear, clairvoyant, healer, and townsperson. In the header files, include the header guards for each. You know how it is. And in the .c file, we are going to include the corresponding header file for the subtype. Also, we will include player protected.h so that protected member variables and functions are visible to the subtypes. Remember, that was the point of this player protected.h in the first place. These subtypes are going to inherit from the player type, so we need access to all the player types' protected functions and variables. Now is a good time to note, don't include playerprotected.h in the subtypes header files, because the header file defines the public API for the subtypes. If you include playerprotected.h in a subtypes header file, then include that subtypes header file elsewhere, say in game.c, it drags in playerprotected.h too, completely defeating the point of having it as a separate header intended for player and its subtypes only. Although you can of course still include player.h in the player subtypes headers if you need access to public player type stuff. And we can compile all our new friends like this. As you can see, this is not a tutorial in building C projects. We are ready for the data bundling step to make the structs for each player subtype. But hold on, how do we achieve our first goal of inheriting from player? We don't want to rewrite the player struct member variables. We do not want to do that. Inheritance in C can be imitated through struct embedding. Struct nesting is when you take one struct and add it as a struct member of another struct. To simulate inheritance in C, you can take the parent type and embed it into the child type struct as the first member. Note that this is not a pointer to a player object, as then the player member would exist somewhere else in memory. Rather, it is actually embedding the entire player struct directly inside bear. That means the memory for player becomes part of the bear block itself. At the moment in memory, the player struct looks something like this, depending on your architecture. But what if we now embed the player struct inside the bear struct as the first member? The full memory layout for bear would then look something like this, implementation defined of course. You see that the player data, the parent type, is incorporated as part of the memory allocated for bear as one contiguous block. Thus, it's almost as though bear has inherited these member variables for itself. In each of our subtype header files, we can add the struct for that player type. Then inside, embed the player struct as the first member so the child type can inherit player's member variables. I've named it super to emphasize that player is the parent type. Do this for every subtype now. Essentially, we've fulfilled goal 1 of inheritance, which is to inherit the member variables and methods of the parent type without needing to re-implement them in the child subtypes. Now these player types need public constructor functions. So you know the drill. In the header file, add the function prototype. Then in the corresponding .c file, malloc him and return the pointer to the instance. And yeah, don't forget to include the standard headers. They're kind of useful. And add this for all the player subtypes. Then remember, when creating the player type, we already wrote this super method to initialize the player member variables. In the constructor of each player subtype, we need to use that to initialize the part of the struct we inherited from the player type. But if we compile this, we get a warning, which is actually an error because you have the where flag turned on, don't you? About incompatible pointer types. That's because the super method expects a pointer to a player type, and we've given it a pointer to a bear. This is not implicitly convertible to a player pointer despite all our struct embedding. But now you're going to see the true power of struct embedding because we can just do this and upcast the bear. Compilers hate this one weird trick. Now it compiles. The reason why the upcast works here is because we embedded the player type as the first member of the subtype. That is the crucial detail. Back to our bear example, because player is first, the player data starts at the same address as the bear struct itself. Casting in C doesn't change any underlying memory, it only changes how the compiler interprets the pointer. Since we made the player type the first struct member, casting a pointer to a bear to a pointer to a player is effectively telling the compiler, hey, treat the memory at this address as a player now, which is perfectly legal as the start of the memory layout for bear is identical to a player. And that's what enables upcasting in C. Plonk, there's initialization in every constructor, and we are now able to construct instances of all our player subtypes. Each subtype inherits the base data from player and can access those member variables through the super fields like this clairvoyant arrow super .player ID. And if you think that this syntax looks a bit clunky, yes, I agree, but don't worry, because we embedded player as the first member of the subtypes, remember we can safely upcast to player star, so then we can access the base fields directly like this. So this feels a lot closer to the kind of inheritance that you get in other languages where the inherited fields can be accessed from the subtype in a more direct way. If you malloc anything in your life, you better free that. Let's make a player destructor. Note that we are going to make proper destructor functions for each individual subtype when we study that concept that starts with a P and ends in polymorphism. But at the moment, every subtype only has a player member within it. So we can just make a generic player destructor function for everybody where we free player protectors. Remember, that's pointed to by the opaque pointer. Then free the player itself. This works because when we upcast a subtype to player start, that pointer still points to the start of the allocated memory block. Where we are at now is we've created the blueprint for all the player subtypes, so it's time to actually construct and add them to the player's array inside the game object. Back in the game constructor, we have this function which allocates room for the player's array, but doesn't fill it yet. So let's now put the constructed player instances into the array. We want to randomize the roles. So one way to do this is to create an array of the roles we want and shuffle them. Fill the roles with townspersons by default. Then drop the special roles in there. We want 2 bears and one of each of the other special roles. Memcopy all those into the roles array. We can shuffle these roles using the Fishy Yates shuffle algorithm. I made a short on this. This algorithm generates a random permutation of the roles by looping through the roles array backwards and picking a random element to swap the current element with. It runs in linear big O of n time, and each permutation is equally likely. The roles are shuffled. We need to now loop through them and construct the corresponding subtype with that role and drop that into the players array. The problem is every subtype has its own constructor. There's no generic player constructor because we want to construct the actual concrete type. We don't want to be constructing a player. Remember, that's an abstract concept. So we sort of need to have a switch here, like if role equals bear, call the bear constructor. If role equals activist, call the activist constructor, etc. A few of you might recognize that we could use the factory pattern for this. The factory pattern is a design pattern where we delegate the work of constructing a specified child class to another method called a factory method. In our use case, we're going to pass in the player ID and role of the player we want constructed into a factory function, and the factory is going to dynamically return a newly constructed player of the correct subtype or role. Then we can simply pop him into the game's players array. To implement this, let's create the factory function called player factory. It will return a pointer to a player type, and it will take in the player ID and desired role. Then inside the function, have a switch statement on the role. If the role is a bear, let's construct a bear instance and return that. But we have to upcast it to the base player type so we can put it in the game's players array. And do this for each type. We need a default case, so let's return null here. Put the function prototype in the player header so the game can call it. Now back in the game construct players method, we can simply call this factory method passing in the player ID and role which is from the all roles shuffled list. We are done. We have an array of players whose roles are randomly generated. As everyone says, you malloc anything, you better free that up. So in the game destructor function, let's loop through the players array and call that temporary player destructor function we made. I promise you we're going to make it a proper one when we get up to polymorphism. I'm really excited now because you've learned about encapsulation, abstraction, and inheritance. So we are ready to start implementing some of this game with the concrete player types. So let's go. Our game loop will continue while there are no winners yet. Game get winner is going to return 0 for no winners, 1 for townspeople 1, and 2 for bears 1. Remember, we can mark this as static to give it internal linkage to show that it's a helper function. If the bears outnumber the townspeople, the bears will win. If the bears have all been voted out, the townspeople will win. Otherwise, return 0. No one's won yet. Next, let's put in some stubs for the night and vote rounds. At the start of a round, the user will be prompted to press enter. Then, if it's currently nighttime, do the night round. After the night round is over, the game reveals the results, i.e. which player got eaten by the bears that night. And if it's not nighttime, do the vote round. And at the end of a round, toggle the is night flag to switch between these, i.e. night goes to day, then day goes to night. If we compile and run this, you can see we can switch between the day and night rounds forever because nothing really happens in these rounds at the moment. Now in the night round, each player is going to take their turn. So they press enter and have their go. We can output the list of players on the screen. This happens for everyone except a townsperson because they don't really have a special ability. So for each player, just output them onto the screen. If the current player we're trying to output is not alive, return because obviously we won't print them in that case. Just print them out. If the outputted player is the current player, put a little U tag next to them. And finally, bears have a slightly different output. Remember, bears can see who the other bears are and which players have been bitten already. So we should create a public function for the bear type, bear output player, for this special behavior. This is an example of how with inheritance, the subtypes can extend the behavior of the parent type. We are going to add this function, bear output player, to the bear.h header file. And then we need to include bear.h in the game. So you can see now when we play it, they can see a list of the other players. The problem is, in the game, every player's actual turn looks a bit different. So, for example, the healer chooses someone to heal, the clairvoyant chooses to see someone's role, and so on. So what would be really great is if we could just call something like player perform special ability or something like that, and the right behavior will be executed automatically based on the player's type. And with that, we get into our final pillar, polymorphism. But first, a summary of inheritance in C. Inheritance is the concept of child subtypes extending upon a base type. In C, a way to imitate this is by embedding the struct of the base type as the first member of the subtype. This allows for upcasting, casting the subtype to the more generic base type. This works because the member layout of the base type and start of the subtype are identical and both begin at the same address. Subtypes can extend the base type by simply adding their own member variables to the struct after the player base type, as well as defining their own methods which operate on the subtype. A convenient way to construct many different subtypes dynamically based on a parameter is the factory pattern. Polymorphism is the concept of subtypes under a single interface expressing different behavior, such as reacting to the same method called differently. There are a few types of polymorphism, but in this video we will cover a specific type of runtime polymorphism called dynamic method dispatch. In this example, there are several quadrilateral subtypes. Each one calculates the area in a unique way. Yet in the main function, you don't need a massive switch statement to call the right calculate area method. Instead, you can just call shape.getArea, and at runtime, it is decided which getArea method to invoke based on the type of the subclass. No conditionals or type checking needed. At the start of a player's turn, a little summary is shown that's like, you are a clairvoyant, select one player to see their role. But notice current player is of the base player type. We want to go something like current player arrow show summary, and polymorphism will dynamically show us the correct behavior for that subtype. And we don't want to have to do any kind of switch statement on the subtype. For example, we don't want to have to do like, if clairvoyant, see the role, if bear, bite another player. No, we don't want to do that. We just want to go player, show summary. Dynamic method dispatch can be emulated in C using vTables. A vTable is a struct of function pointers whose functions are to be implemented properly by the subtypes. The base struct contains a pointer to the vTable, often known as the vPointer. The subtypes which inherit from the base type will then provide their own unique implementations of all the functions defined in the vTable. Each subtype will have its own concrete vTable and will then assign these function implementations to its own vTable's members. This is done during static initialization. Then when a concrete subtype is constructed, the pointer in the base struct, remember the vPointer, will be configured to point to the subtype's vTable, essentially hooking up the subtype's vTable to the object instance. Then, at runtime, the invocation of the correct function will occur by simply following the pointer to the vTable and then to the function in the vTable, known as dynamic dispatch. Okay, I know that was a lot to take in, but let's do it one step at a time. So in the player struct, add a pointer to a player vTable, marked const to show that the vTable will not be altered. This is our vPointer. Actually define our vTable. It contains a function pointer to one method right now, show summary. Remember, this is going to show the player's unique summary at the beginning of their turn. Then for each subtype, we need to initialize a struct of type player vTable, and we will point this function pointer inside to the actual implementation of that behavior for this particular subtype. For example, let's start with the activist. We'll create a global static const variable within activist.c of type player vTable called activist vTable. Then we will point the show summary function pointer to the activist type's own activist show summary function. Let's make this function a stub for now, but it does need to follow the function signature mentioned in the vTable definition and take in a const player star parameter. Quick question for you. Why is activist vTable defined at file scope instead of inside any functions here? Because we need the vTables to have static storage duration. So far, the other player properties like isAlive, canVote, and so on are unique to an instance of the player. This means their lifetime should follow the lifetime of the player instance they're bound to, i.e. created when the player is initialized and freed when it's destroyed. On the other hand, a vTable is different. A subtype's vTable is shared amongst all instances of that subtype. So we don't want copies to be created and destroyed with each instance, wasting memory. We need a single vTable whose lifetime is the duration of the entire program. If any instances of the subtype are freed, the vTable still persists in memory. So that's why the vTable is initialized here outside of any functions. So its lifetime is the whole duration of the program, but we still mark it static to limit its linkage to this activist.c file because this is the activist type's vTable. And remember, all the subtypes are going to have different ones. Let's fill in this show summary function properly. Show summary will say something like player X, your role is blah for all players. So let's start with a default show summary function in the player.c file. Make that available in the player protected header file so it's available to all these subtypes. Now we will call the default show summary function in activist show summary. Then the activist has a special move. You can select one player to stop them from voting during the day. Let's create a vTable for every subtype now in a similar way. In order to use the functions within it, we need to hook it up to each instance of the subtype when they are constructed. In other words, the player type carries that v pointer to the vTable. When a concrete player subtype, bear, healer, etc., is constructed, we need to point this v pointer to the correct vTable for that subtype so that the right behavior is called when we invoke a method in the vTable. That is how we do dynamic dispatch in C. Hop into the super function where we initialize these player struct members. We need to add a pointer to a vTable as a parameter to be set on the player. Now in the constructors of the concrete subtypes, we can simply pass in the address of this subtype's vTable to hook it up to this instance. As this is a raw address, it's important that you marked the vTable parameter const. Finally, the big reveal to tie together all this polymorphism. To invoke this behavior for the current player, go through his v pointer and call show summary, like cur player vTable show summary, and obviously pass him into the function. At runtime, dynamic dispatch is going to invoke the method in the vTable which we hooked up to the current player's subtype. So inside game do player turn, we don't even need to know the role of this player. We can simply call cur player vTable show summary. Now it's time for the big reveal. You can see that polymorphism is doing its job. Each player takes their turn. Now, even though we called show summary on the generic player type, each specific player is showing a different output which is dependent on their subtype. That is so beautiful. This concludes the polymorphism part. So, quick summary: polymorphism is the concept of different subtypes under a shared interface exhibiting different behavior. This kind of runtime polymorphism, called dynamic method dispatch, can be simulated in C using vTables. The base type defines a vTable which consists of a set of function pointers to methods which child subtypes must implement. A pointer to this vTable type is kept as the first member of the base type, known as a vPointer. Child subtypes then static initialize their version of this vTable, pointing to their own implementations of the virtual functions. The subtypes vTables have static storage duration so they can be shared by all subtype instances and last the lifetime of the program. When constructing an instance of a subtype, the correct vTable is hooked up to its vTable pointer. So far, when a player takes their turn, they see their summary, but they can't actually do their special move yet. I added a new special ability function to each subtype, which returns an event, so the game can handle their special ability. The event simply tells the game which player ID was affected and what happened to them, and I made a global default event to denote when nothing happened. The activist bans someone's vote, the clairvoyant sees someone's role, the healer protects someone from the bears, and the bear bites someone. The townsperson does nothing, so I made this default special ability function. I also changed a couple of these player getters and setters. For example, player ban vote now returns an int to denote if it was successful or not, and I created player gets bitten for when the bear bites somebody. Maybe you're wondering, why did you give the special ability functions internal linkage? Don't we want to call them from gamer.c? No, we want to use dynamic method dispatch for these too, as in we'd love to go cur player special move without needing to explicitly call the right special move method for the subtype. So see if you can remember how to do this. We start by adding this new function pointer to the player vTable. Then for each subtype in their unique vTable, simply point this to the implementation for that subtype. The townsperson is going to point to default special ability, which returns the default event. This function prototype can be placed in the player protected header file since we don't need external types accessing it. In the game itself, after you've shown the current player's summary, we get the player to perform their special move. This function grabs a valid player ID of the desired target player. Then we call special ability of the current player and pass in this target player. There's that runtime polymorphism again, which dynamically calls the correct special ability method depending on the current player's subtype. This is in a loop, so we keep prompting while the move was invalid. When we do get a valid event, the game object handles it. If it was a bite, set the player bitten ID to that player. If it was a heal move, set the player healed ID to that player. A few of you might be wondering why we don't just set these game fields from within the special ability functions themselves. The reason is because even if we pass the game object into these functions, they can't access fields on it due to encapsulation of the game object. Remember, we made the game an opaque type to specifically stop other objects setting these fields. Doing so means the game itself is applying these events and controlling its own fields in one place, rather than having other objects randomly mutate these fields. It keeps the responsibilities a bit cleaner. Now these special moves can be performed. The clairvoyant can see someone's role. The bear can bite someone, but he can't bite another bear. Now the other bear sees who's been bitten already. That's due to the bear output player function we made. The next thing we're going to want to do is reveal the results of the night round. We also want to make sure we reset the game after each round, because in the following night, notice player 3 is still marked as bitten, but that should actually be reset. I filled in game reveal night results. It chooses a random player to be eliminated amongst the bitten players, but if that player is the same one who got healed by the healer, no one is eliminated. Otherwise, they just get eliminated. Bow bow. Then we decrement the number of bears or townspeople left in the game. Remember, these counts are used to decide if either side's won the game yet. Then the player is eliminated. This is a generic player method which sets is alive to false. I'll show you how to make a public method for a player subtype. When a healer is eliminated, they get a 50% chance of self-healing and coming back. This method takes in a pointer to a healer. Remember, we can upcast to a player to access base type fields like player ID, and this returns 1 if successful and 0 if not. As this is a public method, put the prototype in healer.h to be included in game.c. Now here's the important bit. As healer attempt self-heal is a healer method, it operates on a pointer to a healer. But in game eliminate player, we are working with a pointer to a generic player type. So we need to downcast the player to a healer. However, the current player subtype could be anything, so we need to explicitly check that it's a healer before we downcast to it. In other languages like Java, you may have seen instance of which performs a similar check. Essentially, all player subtypes extend the player base type, so upcasting to a player is safe, but not all players can be downcasted to a healer because this player might be a different subtype, so downcasting requires an explicit check. This time the bears bite the healer. It reveals the healer got bitten, but he gets a 50% chance of making a comeback. Yay! To prevent the endgame getting too stacked, we want to prevent the activist and healer banning and healing the same players 2 nights in a row. So the activist needs a property last banned, and the healer needs a property last healed. Let's practice encapsulation by making these fields private from the other types. We can use the opaque pointer approach again. Have an opaque pointer pointing to the private data. This is only forward declared in the header files. Then in activist.c and healer.c, define the private struct properly. Give them constructors too to initialize the value, and set them in the activist and healer constructors respectively. Then in their special ability methods, if the target player is the last healed or last banned player, tell the current player they have to choose someone else. Otherwise, set the player ID of the target player to be the last banned and or last healed. For fun, I also set last healed to be the healer themselves if they successfully self-heal. And you see, we can't set these fields from outside the activist and healer.c files. The pointer to the private data is opaque. This works, but there's going to be memory leaks because we added private data to the activist and healer, but all players get cleaned up in this same generic way, as in we never free that private data for the activist and healer. Now, if you're thinking, this would be a great opportunity to add a destroy method to the player vTable and have each subtype point this to their own implementation of a cleanup function so dynamic method dispatch allows the correct destructor to be called at runtime, I'd say, yeah, good one, let's do it. Get rid of this silly generic player cleanup function, we're going polymorphic. I made a player destroy function for cleaning up the player base type stuff like protected data to be called from the subtype's individual destroy methods. Then, to the player vTable, add a function pointer to destroy. Now the fun bit, give each subtype its own destroy method and link it up to its vTable. For the most part, it's the same across types. We'll pass the player base type into the player detour to free the protected data in the player struct, and then free the object itself. This gives us the opportunity now to free the activist and healer private data properly. Then the best part, we can clean up the player properly now by invoking the correct cleanup function in the player's vTable. No more memory leaks. Hooray! Finally, we need to do the vote round where the players vote out who they think the bear is. I allocated an array to store how many votes each player currently has, and max votes keeps track of the maximum number of votes seen so far for any one player and the player ID which has the most votes. We loop through each player and show them this vote prompt. This function returns 0 if the current player can't vote, either because they've been eliminated or the activist banned them. Otherwise, it shows them all the players and how many votes they each have currently. Then we get the input for the player's vote. Remember to -1 to convert it back to 0 indexing before incrementing the number of votes for that player. If that player now has the most votes, set the max votes to that number of votes and their player ID to keep track of who has the most votes so far. Then the voted player is just whoever got the most votes when the loop ends. I couldn't be bothered to deal with ties, sorry. Eliminate the player who got the most votes, free the votes array, and importantly, reset the game state ready for the next round. This involves resetting the game round fields and the player round fields. Finally, the activist gets a lucky 50% chance to vote again after they voted. To implement this, I added a private member variable, voted twice, which stores whether they've already voted twice this round. Then a public function, activist attempt second vote. If they've already voted twice this round, return early. This stops them being able to keep getting a chance to vote again forever. Otherwise, randomly select if they can vote again, setting voted twice if successful. To call the function in game.c, remember we must explicitly check if the current player is of the activist type before downcasting. Decrement PID if successful, so the activist gets another go to vote. The game is done, which is so epic. Let's do a big playthrough and remind ourselves about some of the OOP techniques we emulated using pure C. 8 players, let's go. It will randomly generate those 8 players and construct them using our player factory. This unique summary in action for each player comes from our vTable technique to support dynamic method dispatch, so the correct implementations for those player subtypes are called. The more generic description of the player IDs come from the fact that all player subtypes inherit from the abstract player base type, emulated via Struct Embedding, giving every player a role, player ID, etc. When the activist bans someone, their private last banned field is set. This goes through the opaque pointer to their private data. Same with the healer in healing someone. The special actions return an event to the game, so the game object can handle these events and control its own internal state. That's because the game is an opaque type, meaning the player types can't change the internal state directly themselves, as these fields aren't accessible to them. There are plenty of public player methods in action here, such as player can vote and player eliminate. The activist got a second chance to vote again. That's thanks to its public method and our ability to downcast after checking the type information carried in the role field. We finished the game and implemented many object-oriented programming concepts in pure C, but of course it's always worthwhile to reflect on what we have achieved here by assessing the limitations of our approaches. 1. We didn't enforce true data hiding at the compiler level. Instead, visibility is more enforced by convention. Our version of protected data relied on no one including the player protected header file. Similarly, private data is hidden via opaque pointers. Someone could manually replicate the struct definition and still access those fields. The player abstract class is not truly abstract in the sense that anyone could just add their own constructor and construct a player instance. Again, this is not enforced at the compiler level in our C version, unlike a lot of languages with built-in OOP support. 3. Upcasting in our implementation is not truly safe or type-checked by the compiler. It relies on the base type struct, player, being nested as the first member of the subtype struct, so the memory at the address of the subtype has an identical layout to the player type. This can easily be broken if someone accidentally adds fields before the superplayer field. Then you would get some wacky behavior if you upcasted a subtype to a player, most likely a seg fault. Conversely, there is no automatic runtime type information. To safely downcast from a player to the correct subtype, you need the object to carry its own type information, which is why we had the role member variable. In many other languages, you don't need to explicitly carry the type information as a separate member variable within the object, which is a little more convenient and easier to maintain. 5. The vTable completeness is not enforced by the compiler, as in it doesn't guarantee all function pointers in the vTable are valid. For example, you could remove one of these entries altogether. That is slightly difficult to maintain because if you wanted to add a new method to the vTable, you need to make sure you're adding it to every subtype's vTable too and not miss any. 6. The use of opaque pointers to separate private data away from the main struct creates extra indirection overhead. It's also typically required to be dynamically allocated and not embedded directly because the parent struct doesn't know the size of it as it's an incomplete type. This adds extra heap usage. If you're interested though, you could experiment with other ways like using a fixed size opaque type, but that is a little bit out of scope for this video. 7. I'm sure there are more limitations, but these are the ones which sprung to my mind whilst doing this project. I'm curious to hear opinions from all of you. In spite of these limitations, I found implementing these OOP principles in C to be quite intuitive and honestly beautiful. From a developer perspective, I also enjoyed the level of control I had over the implementation of the OOP patterns, unlike higher level languages which sometimes enforce specific approaches. I'd really love to know your thoughts because this project leaves the door wide open to opinions and preferences. This video is explaining how you could implement some of these OOP patterns in C. However, I'm not sitting here telling you you absolutely should do this every single time. I believe that some projects lend themselves to this design more than others, and others, like the classic procedural way, is good enough. But what this video does give you is a few extra tricks up your sleeve for you to use when you need it. So I hope that it was useful for you. I also hope that this video has helped inspire you to open your mind a little bit. You don't actually have to let your language define what you can and cannot do. And as always, thank you so much for watching.